Okay. Welcome all to this week's episode of the Functional Programming Online Seminar Series. Today we have Stephanie Weirich from UPenn, and she will talk about strongly typed System F and GHC. I'm very excited about this topic, so I can't wait to listen. But before Stephanie starts, I would like to remind you that we take questions through Slido, and the link is in the YouTube chat. Please type in your full name when you ask a question, so it's easy to answer. And there's also a link to the slides that Stephanie is using, as well as the code that will appear in the talk. So if you want to look at that, even during the talk, that's also possible. Okay, so please take it away, Stephanie.
Thank you. And thank you, Koen and John and Mary, for putting together this seminar. Before I begin, I want to hijack things and give a quick announcement about ICFP. So unfortunately, ICFP will be an online conference. So it will be at the end of August. So please do make time during August 23rd through 28th for ICFP. The list of accepted papers was just put out yesterday. So please take a look and see all the exciting talks that we're going to feature at ICFP. And the other thing I want to draw your attention to is that we've announced a call for tutorials, panels, and discussions. And here, this is meant to be a very informal mechanism for you to get a little time on the schedule to meet up with people, to talk about whatever you like. It's important as part of the functional programming community to have talks about scientific papers, but it's also important to have other kinds of conversations. And so we're explicitly issuing a call for that kind of material. So interpret this very broadly, send us a proposal by July 22nd so that we can arrange it and make sure that these are evenly balanced and advertised, and please let us know. And so that said, I want to talk about my talk. So my talk is going to be a little bit different than some of the other Chalmers seminars, if you have been seeing the rest of this excellent series. So my talk is more of a tutorial in nature, because again, I believe that we have lots of room. Tutorials and other kinds of technical discussions are also important for us to have. So my tutorial is going to be based on this very specific challenge problem that I encountered a little while ago, and I had a lot of fun trying to solve. So what is the challenge problem? So the challenge problem is that I would like to create a strongly typed representation of the System F lambda calculus using my favorite programming language. And today, my favorite programming language is GHC. And when I say System F, I'm really talking about a typed language with parametric polymorphism. So we have some way of having polymorphic types. And when I talk about a strongly typed representation, what I mean is I would like a representation of the terms of that language to encode the type system, so that we are only allowed to work with well-typed terms, whatever we are doing with that term representation. The other thing I want to let you know is that, as Koen said at the beginning, my slides and all of the code that I'm going to present today is available on this link that you could see at the bottom of the slide. It's also in the YouTube window. So please do take a look either during the talk or afterwards. And I'll also remind you, when you're on YouTube, you can pause and rewind. So if I say something a little bit too quickly, definitely go back and catch up. You know, there's no need to, because this seminar is online, there's a little bit more, we can take advantage of that. Okay, so let me give you a little overview of what I'm going to be talking about today. Oh, and I should say, why do I have all these dragons on my slides? So when I was young, one of my favorite books was about this princess who decided that she wanted to become a dragon hunter. And so she went out to find and slay dragons. And so that's kind of the metaphor in my mind for adventure now and for challenges, is to go out and find those dragons. So today, the dragon that we are going for is the dragon of the strongly typed term representation in System F. Right? And so how are we going to go out? What is our adventure going to look like? So the first part, So the first part of it is we're going to just start simple. And I want to talk a little bit about just how to represent the simply typed lambda calculus using the Bruijn indices. So here, this is not going to be a strongly typed representation yet. I want to establish sort of the framework that we're going to be using for the rest of the talk. And along the way, as we do this, I want you to pay attention because we're going to develop a general interface for working with substitution for languages that use de Bruijn indices. In the second part, in the middle part of the talk, we're going to extend that. We're going to modify what we've just done, still for the simply typed lambda calculus, but we're going to turn it into a strongly typed representation. And here we'll have to also modify our general interface. But as we do that, what we're going to see is that it's going to fall out that we'll get a proof in Haskell that as we apply a substitution to this term representation, it has to preserve types. And then in the third part of the talk, we're going to take what we've seen in the first two parts and apply it to system F. And so we will get, that's where we will talk about a strongly typed representation for system F. And for this particular part, we're going to be I'm going to draw on this library called singletons. That's going to really help me do the type level programming to express how the system F types work in my representation. There is a little bit of a caveat. This isn't a fairy tale. Not all of the dragons are going to get slain, but it is going to be a fun time. We will have an adventure. The other thing I will say, because of the format of this seminar, with the YouTube stream being 20-second delayed, I'm going to be taking questions at the end of each of these three sections. So after I finish part one, I'll have a chance to answer some of your questions on Slido. Okay, so let's get started. So we're going to go on an adventure. And so how do we get started on an adventure? Well, we might go to the library and look for some ancient text to guide our way. And so here's the ancient text that was very influential for me, right? It was a description of how to create a strongly typed term representation using the Coq proof assistant, using the dependently typed programming language that is embedded in this proof assistant. So this paper is by Nick Benton, Gil Herr, Andrew Kennedy, and Connor McBride. What I've done really is take the ideas in this paper and translate them to the context of GHC. And sometimes I find it's really useful to take ideas that have been fully worked out in one context and put them in another context. And you will learn quite a bit. But I mean, it was a way for me to understand how these ideas worked very deeply because I had to recreate them, but it also taught me a little bit about how dependently typed programming in Haskell works. Okay, so let's talk about the simply typed lambda calculus. And here I have put up the 4 slides, or the 4 typing rules for STLC. This is taken straight from Wikipedia. So we have, in the simply typed lambda calculus, we have variables, constants, lambda expressions, and applications. Right? And so that means our abstract syntax, we need to have 4 different types of expressions, right? So our types that we're going to work with, we're just going to have our base type is going to be some kind of integer type, and then we have function types. In our expression type, we have 4 different kinds of expressions. We have integer expressions, so this is just literal numbers like 3, just some kind of base value. We have variables. This IDX type, this is the type I'm going to be using for de Bruijn indices. And I'll unpack what this is in a little bit. For right now, just think of this as just a natural number type. This is just nat. And then we have our lambda expressions, which talk about what the type of the binder is and the body of the lambda expression, and then applications. So let's see a quick example. So here is a lambda calculus expression that you might want to represent using this data structure. And so here's what it would look like using the constructors that I just showed you. And you can see, even though I have 2 occurrences of x, the first occurrence has 0 lambdas till we get to that binder. So its index is 0. The second occurrence is underneath a different binder. And so its index is 1. So when we use de Bruijn indices to represent variables, we need to count how many binders we go out to know which variable we're referring to. right? So here 0 refers to X. Over here, since we're inside lambda Y, 0 refers to Y. If you're sitting there trying to figure out what T1 and T2 are, there isn't a simply typed lambda calculus types that we can put in for those two binders to make this term type check. We're working with a representation that is not going to enforce well-typed terms. Okay, so this is our data structure that we're using for lambda calculus terms. And what might we want to do with this data structure? So perhaps we want to write a function that tells us how it might reduce using a small step operational semantics. So if there is a beta reduction inside this term, let's find the leftmost beta reduction and return it. If the term is a value, we're just going to return nothing because there's not a way to step this term. So for example, a literal integer is a value, so there's no step that we can return here. But now you see at the top, I wrote in the title of the slide that I was writing small step reduction for closed terms, right? And this is not something that the type system knows about, but I really mean that this function we should really only be calling this function for closed terms. So if I ever get to a variable, a free variable like this one right here, I'm going to throw an error because it's unbound. Lambda expressions, though, they are values, so I don't have to step them. And where we find our beta reductions are inside applications. So if I find an application and it's a closed term, I know there's going to be some beta reduction there. That's a property of well-typed closed lambda expressions. So let's step it, right? And we're going to step it by looking to see what E1 is. So we'll pattern match on E1. If it's a number, that would be a type error, so we can't step that. If it's a variable, again, it would be unbound. Here's our beta reduction. If the function part of an application is a lambda expression, here's where we want to do the action. Here's where we want to do a beta redux. And then otherwise, if it's another application, we're going to call this step function recursively to find the beta redux to do. And the part I want to hone in on is this line right here. How are we going to do a beta redux with this particular function, with this particular variable representation? We're using the Bruijn indices to represent variables. What is the definition of substitution with this data structure, right? So we want to somehow figure out how we can substitute E2 inside the body of our lambda, inside E1, because that's how we might step a function application. And I have to confess here, for a long time, I really found de Bruijn indices very confusing, right? Because there are a lot of cases. And so I'm going to start right now and just kind of walk through all the cases to think about when we're thinking about substitution with de Bruijn indices. And I'm going to be a little bit more general than this particular function. I'm going to talk about substitution even for open terms, because if we're going to define a substitution operation, we want it to work for not just this step function, but any particular function that we're going to use substitution for, right? So in the simplest case, right, we can think about, well, what if we know E1 doesn't have any binders in it? There's no lambdas inside, right? So this is a lot easier to think about, and maybe I can start to understand what's going on. So in this case, we know there's no other lambdas, so every var 0 inside of E1, we want to turn that into E2, right? So we want to traverse the term looking for those var zeros. But there is a little bit of an issue for the fact that E1 could be open, right? It could have some other variables. And when we do this case, when we do the substitution, we're taking this lambda off. And so we're decreasing the binding level of the variables in E1. And so as we do the substitution, we may want to do a little bit of additional work. We may want to decrement all of those other variables to make sure that they point to the right place. So that was the simple case. In the more general case, what if there was a binder under E1, right? In that case, as we traverse, we might find a lambda, and then we go under that lambda. Now suddenly we're going to start looking for var 1 instead of var 0. And as we look for var 1, the variables that are free in E1 are also going to change, right? Because before, outside of that lambda, variable 1 was a free variable. Inside, it's the one we're looking for. So we are going to be, the variables that we're decrementing inside E1 is going to change. And then also, since we've gone under a lambda, we want to make sure that we don't capture any free variables that are in E2. And so we need to also shift those variables at the same time. And that, of course, is all what happens if there's one binder. But what happens if we have n binders that we might have to go through? And again, we can work it out, and we can generalize all those 2's into n's or n plus 1's as we need to, right? And we get a general purpose recipe for substitution. Now, at this point, right, none of this depended on the fact that I was doing substitution for, in particular, for the simply typed lambda calculus. Any kind of typed lambda calculus would have to do this kind of reasoning. Any kind of data, any kind of language with binding that we might want to represent is going to have to think about, you know, which variables need to get shifted in what way. So is there a way that we can take this complication, right, this challenge, and step back a little bit and express it a little bit more abstractly? So at this point, I want to kind of divide our operations up into how I would like to explain substitution using this representation in a way that kind of hides some of that complexity that we just looked at, right? So what I would like to do, what's important to me when I'm defining substitution for the simply typed lambda calculus, right? I need to say what happens at a variable, and I need to say where the binding occurrences are, right? Because that was the two important parts that are really specific to the simply typed lambda calculus. So when I define my substitution operation, I want to say, let's just make an abstract type of what a substitution is. And we'll think about when we get to some variable index, we want to be able to apply it in some way, take that index and figure out what we're mapping it to. And when we go under a binder, we want to be able to modify that substitution, whatever information it's storing, so that it knows that we have gone under a binder, right? So really, this is much more abstract view of the world, and it's going to encapsulate inside just however we define these operations. That's going to encapsulate all of the shifting and decrementing and incrementing that we have to do for indices. Now, there is one problem, which is we're not really a general purpose library yet, because this apply sub operation, right, it's still specialized to the language that we're implementing, the simply typed lambda calculus. So let's generalize a little bit more, right? We'll add a type parameter to our abstract substitution type, and our two operations, right, will take a substitution that is parameterized by what type of result will we get when we apply our substitution. Right, so apply sub is going to it's going to take an index and get us an A if we have a substitution for A's. Right, and lift will just modify that substitution. Both of these operations may need additional information from the language, from the specific language, to be able to implement. And so we're going to define a type class that captures the information that the library needs about the language, like the simply typed lambda calculus. So that type class, so the two bits of information that the type class is going to capture, well, we need to know what the variable constructor for that language is, and we need to know what the substitution operation that we're trying to define is, right? Because, well, we need to know the variable, because whenever we do shifting, we're going to be taking an index, and sometimes we need to just make a new variable that has a modified index. So we need to know what that var constructor is. And then substitution, as we do lifting, sometimes we're going to be composing substitutions together. So we need to know how to apply the substitution operation. So once we've captured this interface, and then what do we else we need? We need the other thing we need from our library, a little bit more in our interface, we need a way of creating substitutions. So for example, if we're just substituting for variable 0 with a particular right-hand side, right? That would be a single substitution. We can create that substitution with, we need some kind of constructors for our abstract type. There are other constructors. If you go and look at the code online that I've developed, this is the one that we need for the talk, but other examples will need other constructors. Okay, so we've created this general interface. How do we use it for the simply typed lambda calculus? We use it by defining that interface and implementation in a separate module. And then when I go over to the simply typed lambda calculus, all I need to do is create an instance for my data structure that says what I need. It says what the variable constructor is, and then it says how to implement the substitution operation. And here I've gotten my wish, right? I've been able, by dividing things up in this way, all of the reasoning about shifting and whether variables are free and binding level, that's encapsulated inside the library. I can explain substitution just in this more abstract way by the instance that I provide for the substitution operation. And it's fairly straightforward, right? The key idea is, again, what's important is talking about where the variable is and when we need to modify the substitution under binders. And you can see this is exactly what we need to fill in our last step of our step function, right? We wanted to be able to do a beta redex in this case here, and we can do a beta redex by creating a single substitution for E2 and then applying that substitution to E1. Okay, so this is the end of the first part, talking about the simply typed lambda calculus. And here I'll look at, now I can take a few questions about this part before I continue. Okay, so the first question on Slido is, what was the dragon hunting book you liked as a child? Oh, I have to give a plug for this book. So this book is called The Hero and the Crown by Robin McKinley. And it's this excellent book because the reason I really love it is because the hero, she's a very awkward princess. She doesn't feel very welcomed by the society she lives in. So she decides to go out and hunt dragons. And she decides to go out and hunt dragons by finding an ancient manuscript of how to make fire retardant. So there's an ancient fire retardant salve recipe, but it doesn't quite work out. So she spends a year experimenting with that recipe, finding the right combination of ingredients until she can develop the fire retardant salve so she can go out and slay the dragons. So that was one of my favorite books. Okay, and then the second question from Adam Sopala is, what if we want to avoid the asymptotically suboptimal behavior of repeated lifting in terms with deeply nested binders? And I have an answer for that, but not until the very end of my talk. So I've given you an interface. I haven't said anything about the implementation of that interface or even slight variants of that interface that might allow much more efficient implementations. Adam is right that just doing this naively can be very expensive, but I have some variants that I can show you. And I'll get to that towards the end of the talk. Okay, one more question. Will I clarify the difference between the error message and the step function and what nothing means in this context? Great question, because that is exactly the segue I need to the second part of the talk. So you notice that sometimes I'm returning nothing because that is when I'm trying to step a well-typed closed lambda expression that happens to be a value. And so that's why I return nothing in that case, because there's no more steps that should be taken. Sometimes I'm using error, and those are cases for I don't even want to call step on this particular lambda calculus expression in the first place. It's not closed and it's not well typed, right? And so I want to distinguish those two outputs. I'm doing it rather awkwardly using error because error is not a very easy thing to work with in Haskell. We want to do better than that. And we are just about to do better than that by switching to a strongly typed AST that is going to help us use types to rule out these errors. Okay, so what our goal for the next part, so for the second part of the talk, is to change our data structure representation so that our implementation of that step function does not have any uses of error whatsoever. And so here's what we need to do to make our data structure representation strongly typed. So I've taken that data type definition that you saw before with the 4 different constructors for expressions, and I've taken that expression type and I've added 2 type variables to it. So those 2 parameters to the expression type are going to represent the typing context and the type of that expression. So what that means, if I have an expression where the parameter is G and the argument and where the first parameter is G and the second parameter is T, I'm talking about an expression that type checks in context G and has type T. Right, and so that context, I'm representing the typing context because I'm using indices to represent variables. I can represent the typing context using a list where the index of the nth type in that list, the nth tie in that list, is going to be what the type of the nth variable is, the nth variable in my expression. So now my expression type can talk about what the free variables of that expression are and what their types are, and it can talk about the entire expression. Right, and so you can see, for example, like the type of a literal int expression, well, it doesn't matter what context it is in, it always has the int tie, that base type. Now, when we get to variables themselves, I'm going to push a little bit of that work I'm going to push a little bit of the work to my substitution library, which we're going to be talking about, because again, I don't want to solve this problem just for the simply typed lambda calculus. I want to solve it for any well-typed language that I want to represent. So so that index type that we used before, we're also going to add parameters to it so that the index type can talk about being an index into a particular typing context. Right, and so if we have a value of this type, we know what type, what that index into that context is, and we know it has to be in range. That context is going to get modified. We're going to do something interesting in that context when we get to a lambda expression. So in the body of the lambda expression, we're adding a new bound variable. So if we want to talk about the body of the lambda expression, having a new variable of type T1, we will use the cons operation to add that to the front of the context to say there's a new variable around that this body is allowed to use to produce a result of T2 when we're constructing a function of type T1 arrow T2. You may be wondering what the sing is, the singleton. It's not going to matter for this part of the talk. I'm going to come back to that later on. So just hold questions about that for now. Okay, so with these 2 parameters, the context and the type of the expression, right, we can make sure that we're only representing well-typed terms. If we have a term that doesn't type check, when we try to construct it with this lambda calculus expression data type, Haskell will give us a type error. Now, how do we do that, right? So let's go look at our substitution library a little bit more. How do we make sure, for example, that our indices are appropriate indices for that context that we're using? So this index type that you see here, you'll notice, first of all, that it's still isomorphic to natural numbers, right? So it still has 2 constructors, 0 and successor, but this time 0 and successor are explicitly pointing out that they are indices to a position in a list. So 0 is the position at the beginning of the list, and successor is a position later on to something else in the list. Both 0 and successor create index terms that have non-empty lists as their context. So we can only index into contexts that are non-empty, that have a place that we can have a type that we can find in them. This is a very standard definition for that you might run across in dependently typed language tutorials. It's really useful for this kind of representation. The thing I want to point out here is that it's a very general data structure in Haskell because it has this polymorphic kind. We're going to be using it in the context of the simply typed lambda calculus, where we'll want to instantiate this index where our context contains ties, the types of the simply typed lambda calculus, but it's going to work with whatever type of data that we put in this list. Okay, so once we do that, once we construct this well-typed representation, strongly typed representation of the simply typed lambda calculus, then let's see how our step function changes, right? So first of all, note the difference in the types of the step function. The parameter for the context, I'm able to put the empty list in here to tell Haskell, check to make sure that I only give closed terms as arguments to the step function, right? There are no variables, no types in this context, so this expression must be a closed expression. And then also look over here. The result type is the same. If I get a result, it's going to have the same, it's still going to be closed, and it's going to have the same type as a type of expression. So we know our step function is also preserving types as well. Right? Otherwise, though, each of the cases that we had before, they're either going to be the same or they're going to be impossible. So before this case was error, now Haskell can tell that this is an impossible case. And I can do this by doing pattern matching. And then Haskell's pattern match compiler knows that there are no cases that I need. This is an exhaustive pattern match because both Z and S need an argument that has a list for the context, for the typing context. But up here, we said the typing context was empty. So neither of those could be constructors that work in this case. So Haskell can tell that this is an exhaustive pattern match. And so it can tell that this is going to be an impossible case. Lambdas are still values. When I have an application, I'm going to still go to this auxiliary function. Now the auxiliary function explicitly tells us that we have a function of type T1, T2, and we're trying to apply it to an argument of type T1. Everything is still closed. And even if we try to apply a number that has the wrong type, so before we had to just throw an error, now Haskell's pattern match exhaustiveness checker knows that this case is impossible, so we should leave it out. In fact, if we try to add this case to our pattern match, we'll get an error saying that it's an inaccessible case. Similarly, we can convince the pattern match checker that there are no variables in closed terms, that we can't have a free variable. We want to be able to do exactly the same code that we did before for creating that substitution, and we want to be able to do the same recursive call. To be able to do the same substitution, we have to go back to our general purpose substitution library, though, and talk about how the type checking works through substitution. Because see, to make this particular line type check, we're taking E1, which type checks in a context that has exactly one variable of type T1, and we're going to substitute E2 for it. And we have to know that that result has to be an expression that has type T2, right? And so our substitution operation, whatever type we give to our substitution operation, it has to guarantee that for us. And so let's go back to our library and add that information to our general interface for how substitution works, right? So before we had this abstract type of what a substitution is, it was parameterized by our syntax type. Now we're going to be parameterized by syntax that is well typed, that is strongly typed. So before A had kind type, now we need to add these extra two parameters to the kind of what our syntax type is. At the same time, we also have to add some extra information to the substitution type to talk about what the substitution does. And these extra 2 parameters, they're going to be 2 different contexts, and they're going to talk about how the substitution changes the context when it's applied to an expression. So what does that mean? So when we go over to our class and you look at the type of the substitution operation in the type class, if we have an expression in one context, so it's in context G1, and we apply a substitution to it, that's going to take that and turn it into an expression in context G2. It's not going to change the type of the expression. The substitution is going to preserve the type of the expression, but it is going to change what variables are used for that the expression refers to, because we might be replacing some of those variables or shifting them or adding them. So it's a very general operation for substitution. And let's look a little bit more closely at the type of the single sub, creating a substitution that just replaces the topmost variable with a term. So if we have a term that type checks in some context G, then a single substitution is going to take terms that type check in that same context with that particular variable of type T, and it's going to get rid of it. It's going to replace it, and we're going to get a context that doesn't have that variable. And this is exactly what we need in the step function, because there G is the empty context, right? And so we need to go and take the body of that lambda expression that has exactly one free variable and replace it so we get a closed term. And so by doing a single sub with that doing single sub with our subst operation, we're going to be able to get the right type here when we use it in the when we use it in our step function. Now let me talk a little bit about the definition of the subst operation, or actually more generally, the instance that we need to provide for the strongly typed lambda calculus term. The code is exactly the same that you saw before. The only difference is these types, which I didn't even have to write, but I added them just to be informative. The types of the operations are a lot more explicit about what is going on. And the other thing to notice is that what is to look at what didn't happen. What if I had screwed up while I was trying to write down the implementation of substitution in this particular version? Like, what if I had forgotten to apply subbed here and just return var e? Or what if I had forgotten to lift? In this case, because our substitutions have much more type information around, I would get an error message if I had implemented my substitution operation incorrectly. So as a library designer, as somebody who's designing a library to support the implementation of substitution for the Bruijn indices, this is fantastic, right? Those types are helping clients of the library make sure that they use that library correctly, that they write the correct substitution term. Okay, so this is the end of part 2. This is the strongly typed expressions for simply typed lambda calculus and the strongly typed substitution library that goes with it. So it's time for a few more questions. So let me look at Slido. Okay, can I encode valueness at the type level to avoid the maybe in step? I haven't really thought about that, so I'm just going to say maybe. Simon PJ, you didn't use all the functions defined in the library, did you? You had a type class and a couple of functions. So there were some other functions in the library for creating other kinds of substitutions. I haven't used them yet. I won't be able to use them all in this talk, but you can take a look at my code online to see some other examples. I have much more extensive examples that also use some of the other functions in the library. And another question from Simon PJ in step app, I omitted the case for int e, but I added a funny right-hand side for var e. Why did I have to do that? Right, so that's going back to this slide here, right, where Haskell could tell directly that that this wouldn't work because the int type created an expression of type int tie, but I was looking for something that had an arrow tie, so that directly Haskell could tell immediately that it wouldn't work. It's because if we go back to our definition, right, int tie directly, int e directly says I need an int tie, whereas var e is indirect. Var e says I need something that's a good index. And so we have to go one level deeper in our pattern matching to get to that contradiction, to show that there isn't a case, to show that there are cases that we can leave out. Right, so it's because there's a little bit of indirection through the definition of this index tie, this indexing operation, is why I need to have that extra level of pattern matching indirection in my implementation. I want to make sure I get through the whole talk, so I'm going to only take one more question next. So this is from Roger Bozeman. This is intrinsic typing, right? Would this approach be possible or even make sense in an extrinsically typed language? So that's kind of the big deal. That's kind of what these strongly typed representations are about, is about how to do intrinsic typing. Extrinsic typing is where you first define the data structure and then you define some predicates on it that refine that data structure to talk about what well-typed expressions are. Mostly people in Coq, for example, use extrinsic typing, but it is very possible to do intrinsic typing in Coq, which is what the Benton et al. Paper shows how to do. Okay, so I will defer the rest of those questions, the rest of the questions on Slido. Maybe we'll have time at the end of the talk for them, because I want to make sure that I get to the end of my presentation. Okay, so let's talk about System F now. So again, I put up the typing rules for Wikipedia for System F. We're going to be taking the simply typed lambda calculus. We're going to be adding 2 new rules to it to be able to take an expression with a polymorphic type and instantiate it, and to be able to take an expression and generalize it with a type level lambda to create an expression with a polymorphic type. And notice here in instantiation, we have to do a substitution in the type to talk about the type of an expression that's a type application. Okay, so here's the start of the data structure. So it's not all going to fit on one slide, but this is the data structure that I want to use for representing strongly typed System F. All right, so far I just have the data constructors that we saw before from the simply typed lambda calculus, and they're pretty much the same that we saw before. And the only change I've made so far is to add 2 new constructors to the types that we're going to. And on the next coming slides, I'm going to talk about the new constructors separately. One thing I want to point out, though, is that I'm going to be using both variants of my substitution library, the weakly typed one and the strongly typed one. So at the type level, I'm going to be working with weakly typed substitutions and weakly typed de Bruijn indices. But at the term level, I'm going to still be working with strongly typed terms and strongly typed indices. So to differentiate, whenever I'm using anything from the strongly typed library, I'm going to qualify that module with S for strong. So it'll be s.index. But up here, I'm using the index type, and this was just natural numbers from the weakly type interface for type level. And this is a little bit of a departure from what Benton et al. Did in their paper. They kept track of the scope of type variables as well, but because I want to use the singletons library, I actually can't quite do that in this particular representation. It's not going to prevent me from developing a strongly typed interface, but what it is going to prevent me from doing is being able to use the type system to talk about terms that are closed with respect to type variables. I'm not changing the parameters of my expression type. This context is still only talking about term level variables. These types, they can have any number of type variables now inside them, and I won't know how many there are just by the type system. Right, and so again, yeah, so I'm using the same parameters, and that's going to allow me to reuse all the same data constructors that we had before, and I can get that reuse by not tracking the scope of those type variables. And I will get very soon, I will talk about what are those two new constructors that we have to add. But before I do that, I want to talk about types, right? So we've added two new types here, or data constructors for types, type variables and polymorphic types, right? And we're going to need substitution for types. And so we can go back to that weakly typed library and define substitution for types just using the structures of that library. So I just need to make an instance of that library for the type data structure and say how to apply a substitution for types inside of types, right? Which really means I do this recursive structure over my data structure, and I apply the substitution at variables, and I lift it inside of a polymorphic type. The big difference here is I want to do this substitution inside the types that I'm using to index the expressions of my data structure, right? And this is just writing functions. So writing the substitution will let me apply substitutions inside of types that I use at runtime, but how am I going to use it at the type level? And that's where the singletons library comes into play. So I'm going to use the singletons library to take these definitions and promote them to the type level so that I can use this substitution operation, not just at runtime, but also in my type system. This is going to rely on me also using this kind of promotion for the weakly type substitution library itself, because we're using things from it, the definition of this type class, apply sub, and lift. But I can do that. I just need to add these brackets around that library as well as these definitions for my type structure. And once I do that, I will be able to use substitutions in the types that appear in the types of my expression data constructors. So I just have, I'm running short of time, so I'm actually going to skip the next two slides, which go into a little bit more detail about what singletons is providing for me. If I have questions at the end, I can go back to them, but I want to make sure that I get to the end of the talk. Right, so this is just talking about the fact that substitution provides this, or the singletons library allows it so that I can talk about subst as a type family as a function that it can appear in the type of tyap. Right, when I have a type application, I want to take an expression that has a polymorphic type. I want to take a type argument, and I want to compute its type by applying that substitution inside that type, right? I'm using this promoted type function that comes just from that little bit of template Haskell brackets that I showed you on the prior slide. The other thing that singletons is providing for me is this connection between a runtime version of type and the T2 that I want to appear in the rest of the type, right? So this is going to make sure that my data structure has something that I can use at runtime if I ever want to look at that type or do something with it in other applications. I won't need it for step, but I might need it for other applications. So I want to make sure that's around at runtime. And then down here for tylam, So that's it for the definition of what the tie-up constructor is. For tie-lam, I want to be able to, inside the body of a type abstraction, I need to increment all the type variables that appear because they're underneath one level of a type binder. And I'm not really going to talk about what that operation is. It's another function that is fairly easy to define. What I do want to get into is the fact that here is where things start to not be as much of a fairy tale, right? So here's where the dragon is really raising its head, right? So let's think about trying to implement a way to apply a substitution for types inside of an expression. So what happens when you apply a type substitution into an expression? Its type changes, right? We're going to be, maybe there are some type variables in that expression. They're going to be replaced by that substitution. And so the result type of that expression, right, is going to be computed by applying that substitution to the old result type. And then the context that expression is well typed in is going to be computed by applying that substitution to all of the types in the context, right? So even expressing the type of this operation gets a little bit crazy, and I'm slightly cheating here just to make this a little bit easier to read. But the implementation has to follow through with what the type says, right? So as I go through all the various cases, when I get to some of the cases that do very interesting things with type variables, like computing like for example, I had to increment the type variables in the context. Now, when I'm doing the substitution, I have to justify this result type that I say that my type substitution function has. And here's where if I just try to do it straight off, I run into a type error, right? I have this recursive call that, of course, I've lifted the substitution because I'm going under a binder as I do this type substitution. So I'm going to get an expression that has this type if you follow through. But when I have a tie-lam is very specific about what the context needs to look like when I use the tie-lam operator. I need the context to look like it's some increment in context. And so tie-lam wants to have an expression where the context has this form. And if I can make sure that it has this form, it will give me an expression, which is exactly the type that I want this case to have. But in order to do this particular application, I need these two contexts to match up. And that's where we really run into trouble, right? Because GHC can't show that these two expressions that are computing the context in that place are equal from each other. And this is not surprising. In fact, in the paper we started with, they mentioned that even in the abstract of the paper, that they have to do a proof at this point, right? This is where the proof assistant really comes into play to show why this particular relationship holds. This is not something we can do in Haskell though, right? Haskell is not a proof assistant, right? I can't go and write a proof that's going to create an equality for these types and dispatch it. So what can I do instead? Haskell's not a proof assistant. Sometimes we can, for simple types of reasoning, we can hijack the constraint solver and get the constraint solver to do that for us. This is not a simple reasoning. And so that's not going to be available for us. Sometimes, if we can't check things statically, we can check them at runtime. But here, that's not really a really great idea because we're putting in this gigantic runtime check in the middle of our substitution function. It's going to be very expensive, and it's a runtime check on data that we don't even have at runtime. So we'd have to go back to our data structure and augment it to make sure we even have the data to be able to do that runtime check. So that's not a very good idea. So the approach that the only way forward I can see is to add an axiom, is to just tell the type checker, trust me, right? I know these types are equal to each other, right? Trust me that they're equal. Use unsafe coerce, but carefully mark that this is an assumption that has to hold for this particular part of the code to type check. Now this is dangerous. I know this is dangerous, right? If I put in an axiom that said that int is equal to bool, GHC could do anything, could segfault, right? This could very well subvert the type system, right? But it's not unjustified, right? I mean, I'm working from a paper that has a bunch of proofs in Coq that this relationship holds, right? So I have a reason to believe that this particular relationship holds. And I can also even kind of convince myself in Haskell. For example, this relationship, I could express it as a quick check property. I could also test it and ask quick check, tell me something I'm not thinking about, right? So there are justifications, so things that I can do to make sure that I'm not going to go wrong. But this is where I really need to be brave, right, in order to get through this part. This is where we're really, where we can't go any further without adding the specific use of unsafe coerce. Okay, so what did we learn? So I have to go really fast here because I am very much running out of time, and I do want to have more time for your questions. And I mean, it's not really news, I think, to some of you that Haskell is not a proof assistant. So it's not going to surprise you that we would get to some place where we need to do a proof, right? And I think examples like this are good to get out there and to record. Yes, here is a place, you know, in Haskell, we did need to have a proof here. And maybe this is a place where we can think about increasing the kinds of internal logic of the Haskell type checker, right? On the flip side, we did benefit. I didn't show you this, but I simplified my definitions quite a bit because I did not have to make the Haskell doesn't have a termination checker. I didn't have to make it happy. So I could simplify my definitions quite a bit. In Coq, the Coq versions were a little bit more complicated than the code that I wrote in Haskell. Because I was working in Haskell, I was thinking like a Haskeller, and I was thinking, you know, let's generalize everything with type classes. I came up with this really nice substitution interface, which I'm really happy, right? And I'm drawing on this long Haskell tradition of general purpose interfaces for substitution. I think Haskell kind of has something to add in this point in the design space. And then the last part is Haskell has an ecosystem, right? There are tools for profiling. Let's answer Adam's question, right? How efficient is this? You know, the naive implementation, how naive is that? And so I spent a little bit of time doing some benchmarking of various versions of this code, right? So the first one, so I did 5 different versions, and I'm not going to have enough time to explain all the variations that I did. But the very first one is sort of the implementation that is in the Coq that was in the Coq paper. Let's just represent substitutions as functions. And there were various changes that I could make to delay the substitutions so that I can combine them together so that we wouldn't have to keep applying them over and over again. And if we defunctionalize so that we know exactly what kind of substitutions we can do, when we compose those defunctionalized substitutions together, we could be a little bit more smart to cut things up and not do extra work. And just to be sure that all of these optimizations still are compatible, I'm doing this all in the context of just untyped, not these first 4, they're all weakly typed, just untyped lambda calculus. The last one, I added some scopes in the types just to make sure that as it was compatible with keeping track of scopes and types in a strongly typed representation, right? And so you can see that it has a pretty significant effect of doing some of these optimizations. So the first benchmark, it's just a very small micro benchmark. I'm not great at benchmarking. The first one, I just generated 25 different random lambda terms. I made sure that, and I did a full normalization, and I made sure as I normalized those lambda terms, I did some substitution. The second one, I wanted to do something a little bit more pathological. I took this benchmark that Leonard Augustin had done a long time ago, where he created this gigantic lambda term that calculates whether the factorial of 6 is equal to this expression. Normalizing this lambda term takes over 100,000 substitution calls. In this particular one, you can really see like this middle bar. It looked good before, but on this one, it's way off the chart. It's up to 14 seconds, but my x-axis ends at 1 second here. So doing all the optimizations does have a significant effect. But yet is still compatible with making sure that everything stays well typed. Okay, so I am pretty much out of time here. I'll throw up the slide, but encourage you to look at it later to see this is just a small bit of related work. There's a lot of related work in this space. Again, this is just an entry point, and I will just conclude here and take some more final questions. Okay, so I'm going over to Slido. So the first question is, you've used a small step evaluator. What changes if you were to write a big step evaluator? I don't think it really would change. I mean, it would be a big step evaluator, and instead, big step evaluation, it can still observe type errors. If you go online in the code that I distribute, I have a bunch of other examples, including full reduction as well. And that's a little bit different because it's harder to observe the type errors in full reduction, but it can still observe unbound variables. I also have some examples of, for example, doing a CPS conversion with this representation, so you can see what it looks like in a different kind of context as well. And so that's also related to the next question. Does anything unpleasant happen if you want to start reducing under a lambda? Obviously, those terms are no longer closed. Yes, again, I have that particular example where we reduce under a lambda. That's available on the code online. There, when we start reducing under lambda, again, we're going to start seeing more proof obligations because we have this context that is non-trivial, and we have to talk about how that reduction works with that. And you can see exactly what kinds of proof obligations we need and how that looks in the example code on the GitHub. The next one is from Ryan Scott from singletons. Can you say more about how the use of singletons prevents you from encoding how many type variables are in a type? Okay, yeah, Ryan, you're calling me on this. I didn't actually try it out. Maybe you have improved singletons so that it can also promote gadgets as well. I don't remember. That would be fun. Let's try it out. Adam asks, the Wikipedia, oh, no. Oh, okay, here. Adam asks, the Wikipedia typing rules already seem strange for not tracking type variables in context. Why is that not problematic when you go strongly typed? Partly why, yeah, so that is a good question because that was a design choice I made. I didn't track type variables. And that's specific to system F. So partly it's not problematic because there's no kinds. Every type variable has the same kind. And so it's really hard to mess up the usage of type variables in system F terms, right? If you have extra type variables, you just have an open system F term instead of a closed system F term. And you can see whether it's open or closed by just looking at the particular type you have if there are type variables in it. All of the examples I was working with today, like the step operation, preservation, and progress that it's related with, those don't care whether the system F terms have free type variables or not. They still hold all the same. Adam also asks, has this library been applied to a program transformations like you find in a compiler? So the example I have in my GitHub is CPS conversion. So this is an example of a program transformation that you might find in a compiler. And you can use this to show that that program transformation is well typed. And I should really actually go back to my related work, which I went very quickly, and highlight this amazing paper from ICFP 2008, where the authors represent system F with a strongly typed term representation and created a type preserving compiler using the features that were found in Haskell in 2008. So again, I'm not working from scratch here. There are other examples that we can look at as well. Richard Eisenberg asks, do you think this approach would extend smoothly to system with type variables of varying kinds? So if we went from system F to F omega, what would we need to know? Right, yeah, so when we go to F omega, then I would need to be able to have the singletons library, be able to promote my strongly typed substitution library, as well as the weakly typed substitution library that I did here. For simplicity, I just promoted the weakly typed library, but I could change if I made this data type representation into a GADIT, so I could keep track of the kinds of these types as well, then I would have to use that strongly typed substitution library to work with it. Okay, the var-e cases have case in of empty in the right-hand side. This is a question from Stefan Fehrenbach. Can we avoid that by marking the fields tricked? Oh, that's a good question. I haven't tried that. Download the code and give it a try. I will have to try that. Oh, there's one more. Oh, Kuhn is telling me I missed a question. Oh, yeah. Sorry, I'm scrolling on Slido and I missed some questions at the top. Okay, David Christensen asks, would it be technically feasible to add an AGDA-style absurd pattern to GHC Haskell? I'm interpreting that as meaning, so in AGDA, when you do a pattern match and there is no cases, you can say that in the pattern itself, instead of having a right-hand side, you just say there are no cases in this particular pattern, right? And I think this step example is an example that would benefit from this kind of pattern match. So I think maybe yes, haven't tried it. Maybe that would be a good thing to add. Philip Wadler asks, can you go back to the 2 slides I skipped? And I apologize for skipping them, but I wanted to make sure that I got to the end of the talk by the end of the hour. But let me see, where are my slides? Right, so these 2 slides I skipped are talking about when we do the singletons promotion. So when I go to code like this is just normal Haskell code, and I wrap it in the singletons bracket, what does singletons generate from that? Singletons is going to take those 2 definitions and it's going to produce some code for me, right? And those 2 slides are just showing what gets produced in that case. So the first thing that gets produced is what's called a singleton type. This is the runtime analog of some compile time data. So this is another GADIT that goes along with TIE and exactly mirrors it, except that the type of this GADIT tells you exactly what that parameter is. I have an example in just at the bottom of the slide. At the same time, to make, so this GADIT that's called STIE, this is the singleton type for TIE, right? It's singleton because there's like, if the parameter for STIE is a concrete type, like int arrow int, there's exactly 1 inhabitant for it. It's a singleton type, right? We know that it has to be the int TIE arrow int TIE, because that's the only term that's going to type check with this type. And every data type that we work with singletons has an analogous singleton type. And so singletons organizes them by having this type family so that we can just always call it sing instead of saying STIE here and SINDEX and SSUB. We have this uniform name for all of the singletons types that are produced by the singletons library. Right, and that comes about by saying for any type, there's a singleton type for it. And in particular, if the kind of this type is this TIE, then the singleton type is STIE. So this is a kind index type family. So that's the first thing. It's explaining how singletons generates, the singletons library generates singleton type. And then the second slide shows what happens for the functions that were involved, right? So as well as generating that singleton type, we get type level analogs of the functions that were in the brackets. So like the substitution function gets generated as a type family in various instances for the pattern matching. And in addition to the type level version, we also get a singletonized version of the function, which is a substitution function that if you know what the type argument is, you know what the substitution is, or you know what the substitution is, you know what the type is, it's going to produce the singleton type that is the substitution of this substitution applied to that type. Again, this is just generated by the singletons library, and it's useful in some situations when we are working with these singleton types. Okay, so those are the 2 slides I skipped. I have maybe just a few more minutes for questions, so I'll try to answer as many as I can. So the next question is by Artem Pelenitsyn. Could the work in Ghost of Departed Proofs play a role in safer interface to adding axioms to GHC in this case? I don't know the answer to this question. I'm not quite sure what the mechanism in the Ghost of Departed Proofs paper is. The next question is by, I apologize for if I mispronounce your name, by Gallet. Missing equation, could you not add a new case to the definition of the type family map corresponding to the commutation lemma? So you're talking about, so this question is in reference to this particular property that we needed. And so that would be going and modifying the definition of map that says if I have this particular argument, it should produce this result. This doesn't really work for a number of reasons, right? So map is this, comes from the singletons library, right? This is the promoted version of Haskell's map function. So I don't want to modify its definition, right? In fact, I don't even have access to this definition. And even if I did have access to this definition, when you are defining type families, you can't have patterns that refer to other function applications. You can't pattern match against applications. So I couldn't even if I had written my own map, I still couldn't have written this definition. Okay, so the next question is, why not use lifted data type equality for type level equality proofs? I'm actually using, I didn't say this at all, but I'm using data type equality to encode these type equality proofs that I need. When I create the axioms that I use in my definitions, I'm creating a member of the type provided by data type equality. So that is an important ingredient. Okay, another question, how do you know where to sing? Why in LAM but not in app, for instance? Yeah, so this is a question about the sort of definition of the strongly typed data structure. You need to sing whenever you use as part of your data structure in 2 ways. If you want it to be available both as a runtime component of your data structure and also later in the type when you need a name for that component of the data structure to talk about a type of a later component. Sometimes I like to abbreviate the type sing using the letter pi because it shows up in exactly the same places you would use a pi quantification in a dependently typed language. Philip Wilder has more related work. There's tons of related work to this, so please do take a look at it. I will see the Slido questions after this all is over, and so I can add this related work to the repo where I have a little bit longer of a bibliography. Okay, so the next question is, how difficult would it be to take a weakly typed term and quote it back into this strongly typed representation? That's not difficult at all. And in fact, I have an example of that in the repo. Oh, Kuhn is saying I need to stop. I have an example, right? So if you can take a weakly typed term, you write a type checker, and if it happens to type check, you can generate the strongly typed term. So yes, it's not difficult, and I have an example that you can take a look at. I'm sorry for the last couple questions. We are really out of time. This has been so much fun though. And I thank everybody for all of the great questions. Please do take a look at the repo, send me pull requests, ask me questions, send me email. I'd love to talk about this more, as you can tell. But
okay.
Thanks again.
Okay, Stephanie, thank you so much for this great presentation. So let's thank the speaker. Right, so so this was actually almost the last presentation in the series before our summer break. So be sure to watch Jeremy Gibbons next week, which is the actual last presentation before the summer break. And we're still contemplating if we should continue with this series after the summer or not, but we have not decided that yet. So thank you, Stephanie, and see you all next week.